only two. Okay, so this is what we've been doing. We've been trying to find out how a spherical curve bends, provided you tell it that you have generators, in this case on the left-hand side, that are parallel. Okay, and what the generators do is it basically tells you what shape this thing is going to bend into. So if you have parallel generators, you're going to bend it into a cylinder, because at every point of the cylinder, the generators are going to be in full contact with the tangent plane. Okay, if you were going to bend it into a cone, the generators won't be parallel, but they'd like spray out, and so you can actually see what the shape of the thing you're going to bend it into is from the way you specified the generators.
So if we were to look to the right-hand side where it's going to form a cone, is the lines just going to go to the other side of the red line, or is it going to be like a little sun with rays going out?
We will do that in painful detail now. Okay. In fact, it can move sometimes, the generators as well. So what we did was we said, fine, this is the curve we're going to crease it along, our crease fold. These are the generators. And then we said, what do we immediately know? If we specify the generators, we immediately know the relationship between T dot RL. In other words, the angle between the tangent and the generator. That's not going to change, because they are both within the surface, and regardless of whether you bend the surface up or not, it's going to remain the same. So we have this, and then what we said is also our geodesic curvature, or the curvature restricted to the plane, is just equals to 1, because our sphere that we made here has got radius 1. So if you had another curve, you would have to actually work out how that thing depends on arc length. And then we said, fine, the total curvature of the deformed surface is going to be greater than equals to 1, because if we don't deform it at all, it's equals to 1. But if we deform it some, then we have that kappa g is simply kappa cos phi over there. Okay, and so we immediately have that inequality that the full curvature in our three-dimensional deformed curve will always be greater than the geodesic curvature. And then we went about and said, fine, let's fold it into a cylinder. And the way I folded it into the cylinder is I made use of the fact that my principal vector is always orthogonal to my ruling. Okay, so when I'm folding it into a cylinder, there's another vector over here that's always orthogonal to the ruling direction, and that's the one that's going to curve. Okay, so it's not an accident that I drew this cyan line that I later used to actually write the formulas down. It's guaranteed that the other direction is always orthogonal to my ruling direction, because that's the feature of your principal directions for a surface embedded in 3 dimensions. Okay, and that comes directly from the fact that you're solving an eigenvalue problem with symmetric matrices, in 2x2 symmetric matrices. Okay, so then I said, fine, we distort this line into our cylinder. We have an expression for the coordinate y in terms of the coordinate on the surface, sine s, okay, and that's y. And then we can therefore have our distorted curve have this relationship where we have it equals to rho sine of y over rho, like I explained over there, and y is just sine s. So we have an expression for our distorted curve that we now have, and here I've simply added the midpoint of the curve as well. Okay. And so what we then have is our crease, okay? The x-coordinate, which tells us where we are along here, remains unchanged, but then the actual coordinates of these guys have been folded up onto the curve themselves. Okay, so we now have an expression for the crease, and now we can go, and because we know what our space curve is, we can work out all the details about that curve. We can work out the tangent by differentiating it. We can work out the curvature, we can work out the binormal vector. And we're going to do all that stuff because we know that our conditions for matching over the crease is dependent on the crease's geometry itself. So let's have a look and see over here. So let's see exactly what it does. Here's our distorted circular curve. So this is orthogonal to my rule direction. There we put it in. Yes?
Can I ask a question, but it's something that I guess we should have done at the beginning of last lecture, but I just want to confirm this is only for developable surfaces.
Yes.
Okay.
As you go through the stuff carefully, take a look at what assumptions go in at every single point, right? The fact that the principal directions are orthogonal is not just true for developable surface, it's true for any two-dimensional surface embedded in 3 dimensions. Okay, so that's true. This, the fact that your ruling tells you that you can bend it into a cylinder, that's true for developable surfaces only. Okay, but differentiate. I've tried to make it as modular as possible, but you'll actually have to go through it carefully and find out. But what I'm saying now is just developable surfaces. Okay, so we have a distorted curve, and we can then say not only the curve at x equals to 0, but at any x, we simply fold them into a cylinder. Okay, and the rule is simple. The angle that we folded into the cylinder is everything that was flat up to there that we've simply now bent up into the cylinder. So the distance along from the y equals to 0 to y equals to that point over there, that distance is exactly the same as the distance along this curve up there. Okay, so here's our cylinder. And then we go and we can plot. This is a sort of parametric plot of this distorted curve that we derived. Okay, and then before you go on, you can verify that the distorted curve is still arc length parameterized, and therefore the tangent, and this is why it's important, the tangent is a unit vector. Okay, and remember the ruling is now also still parallel lines in the minus x direction, so there it is, it's just been lifted up, because remember the ruling is a vector and you've now changed the base of where the vector is, but it's just bent up. Okay, so you can see that this ruling is literally stuck on the page. You've basically taken this ruling and you've bent it up, and that's what these curves would be like. So if you were to, on my little prop, they actually use the rule surfaces, they would just remain stuck on the page. Okay, so now we go on and we work out the properties of the curve. So you can work out the unit tangent vector parameterized with S. We can then do exactly what we did in the problem sets, work out how that changes, because we want the normal vector. And so the normal vector is simply the change of this thing divided by, to make it by its magnitude, to make it a unit vector. Okay. And we can work out the curvature of the surface, which is just 1 over rho. We can work out the kappa p, in other words, the thing I worked out, the component of the curvature that's projected normal to the plane is just this. The full curvature of this curve over here, in other words, if you take t dt ds dotted in with itself, and you simplify it remarkably, it's 1 plus sine theta rho squared. Okay, so you've basically taken kappa, right? So you can see here's the curvature. There's a component that basically comes from the fact that you had a circle plus the fact that you are distorting it with into a cylinder. Okay. A word of advice, when you do these problems, simplify these things as much as possible, because it makes it easier for you to go on. Okay, so I actually had problems doing this in mathematics. I did it by hand, and then I got a very sweet answer. So maybe practice on this thing before you do the problem set one, that you can actually see what tricks lead to these simplifications, and you can make sure your method of working is solid. And that's basically why I put in all the details as well. So basically your kappa is just the norm of your dt ds, the unit, how the unit vector changes with s. And that is just also, here I've switched theta. Remember theta is equals to pi over 2 minus s. So that's just switched over there. That's how the cos switched to sine. Okay. And Then we have our normal vector is just the unit vector in the dt ds direction, so I divide by kappa. And I can work out my binormal vector is just t cross n. Okay, so I literally take this dt ds, work out the cross product with that thing, divide by kappa and simplify it. And there, just to make sure your practice is working, I give it to you so you can check. Okay, it's not pretty, but it turns out that there's a structure to it. Okay,
and
so
that big N is a normal vector.
yes.
Yeah, what I mean is it's not necessary to normalize it.
Do normalize it. Otherwise, a lot of the other stuff gets confused.
Yeah.
Okay, so the trick working with a curve is you get the curve, then you set a triad of normal vectors on them, or normal unit vectors on it. Okay, and then what you're going to do is, in order to work out the other ruling direction, you've actually got to go into the triad of the curve. Okay, so what you then do is you take this ruling direction on the left-hand side, and very beautifully simple, you now butcher it by expressing it in terms of its components of t and b and n. Okay. And so because those are the components that then flip over eventually and cause the other make the other ruling directions. So remember, we had that r in general being expressed as cos theta t plus sine theta times, maybe you should just write that on the board for me. I think it's in the notes there if you've got it. That you have basically your ruling direction. Remember, we had that normal expression for it, that r is equals to cos theta t.
So r
is equals to cos theta t. The unit vector, yeah, without the dot, plus sine theta. Then it was, do you have it in front of you, Kola?
R is cos theta t plus sine theta
times
bracket n cos phi. N cos phi.
You can erase the other stuff.
Plus.
Don't let the previous class intimidate you.
Your bracket n cos phi plus b sine phi.
Yeah, okay. So what we have now is, so you can see if you have, we have what t and n and b are. Okay, we've worked that out for our particular curve. And we have what r is. Okay, and so we want to work out what these angles are on the left-hand side. Okay, so we work out t dot rl. Okay, and this is the reason why you had to make t a unit vector. Otherwise, you're going to add you're going to start getting complications when you work out the dot products. Okay, so you have t dot rl is simply cos of theta l. Okay, but that's the formal thing that we're going to use. But you already know what t is, and you already know what rl is. So simply going back, right? Right, so here's t is simply minus sine s, rl is just minus 1. So t dot rl is simply sine s. Okay, and then so you immediately from this expression you get that theta l is pi over 2 minus s. then you work out n dot RL. Okay, n dot RL, just from your definition of R, is simply sine theta L cos phi L. And you get that that is equals to cos S over kappa. It's just the first component of what n is. Okay, and then you do the third one, you have B dot RL. Okay, so that's simply, once again, from your general expression, it's sine theta L times sine phi L. And you know that that simply is, from your expression for B that you've worked out, is simply minus cos to the 3s over kappa rho. Okay, so you have expressions for cos L and the cos theta L in terms of S, which gives you theta in terms of S. You have an expression for cos phi L in terms of S, and you have an expression for sine phi L in terms of S.
Can I ask maybe a stupid
Yeah.
question? Is the angle S or is the angle S over kappa?
No, that's cos, I would have put brackets around it. It's cos S divided by kappa. Okay, and this is cos to the 3s divided by kappa. Okay, so then you've now got cos of phi L, and it's just useful eventually to work out tan of phi L just by dividing this expression by that one. Okay, so you can work out what phi L is. Now, so that's the ruling lines on the left. The ruling lines which you know and which allows you to establish what these angles are. The ruling lines on the right you don't know. This is what we're going to determine. And this is how you're going to see how we would determine it, and the fact that in fact it is completely determined by the ruling lines on the left. Okay, so we write out the general expression for the ruling lines on the right. Here it is, except that now the angles have different names. They're different angles. Okay, so what you have these joining conditions. You have the fact that the curvature, it's the same curve. In other words, the same circular curve that you had on the left-hand side is the same when you make the join that's projected into the surface, is the same circular curve you've had on the right-hand side. That's common, right? So you know that the curvature on the left must be equal to the curvature on the right. Okay? You also know that the total curvature of the distorted curve kappa is the same. Okay, so you immediately get that cos of theta r must be equals to cos of phi r must be equals to cos of phi l. Okay, so those are the same, nice and easy. So you already got what this component, what that aspect of your ruling direction is. You have that the curvature projected normal to the plane. Remember we had the result, the magnitude is the same, but they differ in signs. Okay, so you have kappa p on the left is equals to minus kappa p on the right. And so what you're going to have is sine phi r is equals to minus sine phi l, and you know what this is already, right? Sine phi l, you can simply get out of there. And now, so you've totally defined the cos r and the sine r. In fact, you don't even have to work out the particular angles. You can simply take it from here and simply copy it back in there. Okay. So, but what we still don't know is what theta r is. Okay, and remember the interpretation of theta r, it is the angle that the curve has, or the direction has with the tangent vector, the angle with the generator has with a tangent vector drawn onto the surface. So we now want to go and determine what theta r is. We already know what theta l is, but we want to know what theta r is. And what we use there is this condition that you have a developable surface. So your developable surface, this condition holds for both the left and the right sheets. Okay, so we can check first of all that it holds for the left sheet. And this is not necessary every time, but it's useful that you just know how to make the calculation. And that I should sort of use it. So let's look everything that's in here. Kappa for the left sheet is simply kappa squared 1 plus cos squared s over rho. In fact, this is kappa for both sheets. Okay, tau which is a property of the curve, so it's also the same for both sheets, is simply minus cos S sine S 2 plus kappa squared over rho kappa squared, which I got from differentiating B and then dotting in minus N. Okay, so that's how I got this, and I simplified it. So we've got what tau is. Now we want to work out what phi prime is. Okay, and to work out what phi prime is, okay, I know that phi prime for the left hand side is simply, I've got several expressions for it over here, right? I can either differentiate cos of phi L, or I can differentiate tan of phi L. In your problem set problem, there's reasons to differentiate this guy rather. Okay, because if you differentiate tan, you may not always know what sine of phi L is beautifully. It might not have a nice expression. But if you take this ratio, you're always going to get tan of phi L. Okay, so you've got tan of phi L, so you can differentiate it with respect to the arc length parameter. And so you're going to get basically an expression for phi prime of L. Okay, and in this case, what you're going to get is simply you differentiate whatever expression you have there, because you know what kappa is a function of S, and so then you're going to simply get that phi prime of L is simply basically using this expression. So dds of cos phi L is simply minus sine phi L times phi L prime. You're going to divide by sine phi L, put whatever expression you got in here, and solve for the phi prime. Okay, so you can get an expression for phi prime of L. And this is what it is for this particular case. Just check that you get the same. Okay, and if you then go on and you put in all these things, you've got everything you need now. You've got tau over there, you've got phi prime over here, you know what sine theta is, okay, and you can check then it's equals to kappa sine phi cos phi, and it cancels beautifully. Okay, so this expression holds for your left hand side. Let's now use it to fix what theta is over here on your right hand side. Okay, so what you do is you solve for theta r, and the way you do it is you simply divide. I want the nastiness above the line, so I wanted to keep this on the one side. So I divided by sine theta. So there I got cot theta, and then I divide by kappa sine phi. Okay, so I have an expression for cot of theta r. Okay, and now I know that tau and kappa are for the curve, and that's common, so it's the same, you already have those as functions of S. I know that phi r is simply minus phi L. Okay, because I have these expressions. So phi prime r is simply going to be minus this thing. And I know, once again, that sine of phi r is simply minus sine of phi L. So I have that. And so I have absolutely everything over here on the right-hand side already in terms of S. And that's why calculating these guys, checking that this thing actually holds on the left is so useful, because in doing that you actually get everything you need to work out what cot of theta r is. Great. So now what I get is, there you can see I've simply replaced my r's with a systematic argument of what the equivalent is with L, which I know. And then I go and I substitute in what I actually have for them. And so I now have cot theta r in terms of S. And now I can express my ruling direction. So this is my ruling directions on the left that I got just by dotting the things in. Now the ruling direction on the right, I found it easier to express it like this. Okay? And look, if you look at that thing that we have there, all I've done is I've divided by that general expression by sine theta. Okay, so it's exactly the same. The reason I've done that was it was very easy to get cot theta r in terms of s. And I have these other two also in terms of s. And what I can do now is I can work out the direction correctly and then just work out its norm afterwards and then divide that to get the unit vector, because I know my RR is a unit vector. And there's actually a better way. So then I basically go, and there it's expressed on terms of the triad of the curve, all the components of the triad of the curve. And what I can then do is I know what T is, I know what N is, and I know what B is. They depend just on that curve. And so I can then say this times T plus 1 over kappa times N plus cos squared S over rho kappa times B. I multiply that out with the actual components of the curve I have in terms of X, Y, and Z components. And then I simplify it. And then I simply get that it's a very nasty expression until you stare at it. Okay. And then once again, I go and identify the things that appear a lot. There's that. So then I can write it down, every single component, my X component, my Y component, my Z component. Okay. And then I can square them all to get the norm, right? And that's simply 1 plus kappa squared plus 4 over kappa squared sine S. Okay, and then I can divide by the norm to get my unit vector, which is just RR. Just check. So this thing must then be equals to 1 over sine of theta squared. Okay, that's just another check, and it is in fact, because you can work out 1 over sine of theta, that's cosec squared, and there's a relationship between it and cot. Okay, it's just 1 plus cot squared or something like that. Sorry, this is, cosec squared, and I think that's just 1 plus cot squared. But that relationship is actually what you see coming out here, so it's just a check. And there you effectively have it. So you can then go about and you can plot these components for the ruling direction, and those will be the components of that actually lie the ruling lines on the surface. So we did that, and to my tremendous relief, it looked right. Okay, so there's our crease pattern that we've bent up. There's the ruling lines on the right that had such a funny expression in terms of the T, N, and B, the triad associated with your curve. Okay, then what I did is you went and go and you project this RL onto the T, N, and B. Okay, so that's that expression. Then you use these components to structure the components of the other ruling direction. Okay, and then you got this. Okay, where you have the cot R is the only really complicated one. You have to figure it out, as well as the sine R. But we've done that. Okay, so there we go. There's the cot R, there's the N. Okay, and you can see immediately I've simply switched the sign of this thing and multiplied by, or sort of divided by sine of theta. So there we go. And then what I did in the previous slide is I simply put in what I had for T in there, put in what I had from N in there, and put in what I had for B in there, and simplified the components. Okay, and here you can also see that you can take the norm of this thing even on this strange basis, because you have T and N and B are orthonormal. So the norm of RR over sine theta R is simply the sum squared of these components, and that's just that. Okay, it's just another verification of the fact that R is a unit vector, T is a unit vector, N is a unit vector, B is a unit vector. Try and keep them unit vectors, otherwise you're going to make your life miserable. You can do it without, but then you've got to track the angles. So best keep unit vectors. Okay, and then you substitute in what they are to get actually the components for on your Cartesian basis. And when I do that, this nice thing happens. You may not, in reality, sometimes you don't always see this. Okay, then just plotting the vectors is fine, right? If you plot the vectors and it looks right, then it's right. But it's much easier to write down and check if you actually do go for the simplified versions. Okay, and here then is your components in your X, Y, and Z. Okay.
So if we plot it, should we still multiply by the sine theta r?
Plot unit vectors for the generators. Okay. So you want to plot the unit. The reason is when you're plotting in 3D, the graphics programs foreshortens it, and it actually helps you see the surface more clearly if you know you've got a unit strip going around. Whereas sometimes you can confuse a foreshortened vector with a vector that's actually just shorter. So plot unit vectors when you plot, because like here you can see that's a unit vector going there, and you can see this is not, you don't change the direction, but if you were to like rotate it, you would still see that all the vectors are the same length. Okay, so then plot these guys. Okay, that is RR. So these are all unit vectors that I've plotted over here for a rather extreme cylinder. Okay, so what I've plotted here is basically these guys. This psi is my sine S over rho. Okay, and so you can see that you are actually getting what my little model predicts. Right, it's really doing that. So, questions before I go on? Yes.
So, I want to say the component directly on the x-axis. Like, does it point up or down directly?
Yeah.
Yeah.
That should be pointing down.
Down.
But it's for sure. But look, it's like pointing skew down, but you're seeing through the surface. So that's why I said plot unit vectors. Otherwise, you're going to add more confusion than you need. You can see it's literally basically pointing away from you. So it looks very short, but it's also, it's a unit vector, so it's pointing far away from you. And then what I found useful, actually, this whole thing is parameterized by rho. Okay, wherever rho is over there, it's the cylinder. And you can actually now plot the thing for various rows and see how it changes. And so that's kind of cool. So here, when rho is very large, right, your circle is very big and it's basically flat, this is what the unit vectors looks like. Okay, there's the ruling directions in the one side, here's our ruling directions on the other side, and now what I'm going to do is I'm going to change rho. In other words, I'm going to decrease rho, so I'm going to make my cylinder more and more curved. And there you can see it actually changing. Okay, so you can literally see the thing go and do this as it curves. Looks like a bird flight. And that's not an accident, right? If you think of a bird, it's literally an armature like the wing with feathers, and the feathers are the ruling directions. And so when it flaps, it's a very simple model for a bird.
So in the case where it's like flat, where it's on the y-axis, let me say flat on the y-axis.
Yeah.
So then it's like a sun with rays pointing out.
Yeah, it's your cone.
Yes.
Yeah.
Okay. And then as it curves.
Changes. It still changes. It goes almost, yeah. And then this is just from a different angle. So there you can actually see it flipping over and folding back like that. So it's exceedingly satisfying to plot. So the problem set, I've said, do a parabolic curve rather than a circular one. Okay, so, and it's also going to be very similar with ruling directions on the one side. The reason for that was the cost is you no longer have a nice arc length parameterization. The benefit is that the algebra turns out to be somewhat easier. Not much, but somewhat easier because you're dealing with polynomials instead. So you don't have to see that type of K thing that I saw. Okay, it was just easier for me to work out. So I've given you that one to do. Okay, and that one I'll give you this afternoon. I'll put that up. So go through what I've done here very carefully. Make sure you can get the same thing and maybe get a method of plotting it. And then try your own one. Okay, so there's only two problems in the next problem set. The one is to get the parabolic curve with a certain ruling on the one side, and then the other one is simply sort of a derivation for principal curvatures, a principal curvature example.